Let's review chapter 1. What were the basic ideas in this chapter? And yeah, we covered a lot of material in this chapter, and yeah, there were some difficult ideas. Alright, so first we looked at propositional logic. So working with propositions, so proposition P must be true or false. So just two options for a proposition. You can combine propositions. So we have these logical operations. So and looks like this, or exclusive or, implication, if and only if. Yeah, so these five, they take two propositions, say P and Q. And then this last one, not, yeah, that just applies to one proposition. It just switches its truth value from true to false or false to true. Okay, and yeah, for these logical operations, yeah, you do need to kind of memorize the truth tables for these. So for example, P and Q, well, there are four combinations, four possibilities. This whole thing is true just in the case where P is true and Q is true. If one of them is false, then the whole thing is false. Alright, so yeah, so go back over those truth tables. So make sure you know these operations. That was in the first section, 1.1. Alright, so an example, use propositions and logical operations to express this. Alright, so we have a sentence. I will go for a walk if it is warm and not raining. Alright, so that makes sense. But how do we write it using these guys? Well, first we need the propositions. Okay, so we're just breaking up the clauses here. So I will go for a walk. So that's a statement. Yeah, it's going to be true or false. And then these two statements are talking about the weather. Q says it is warm. R says it is raining. Okay, so these are good propositions. They're either true or false. But how do we connect them? So what logic do we need? What logical operations? Yeah, we see an if, so that means there's an implication. And we see an and, so there's the... So we're going to need these two. But yeah, as you notice with the homework, you have to be careful. So I will go for a walk if it is warm and not raining. So which part comes first in the implication? Well, maybe a good way to see it is to sort of rewrite that sentence. If it is warm and it is not raining, then I will go for a walk. Okay, so this makes it clearer that, yeah, it's this weather part that comes first. So if P then Q, that's P implies Q. Yeah, here we have if this stuff, so if it is warm, that's Q, and it is not raining, so we need the not, so not R. So if Q and not R, then P, then I'll go for this walk. Alright, so yeah, so it's not P implies this, it's this implies P. Okay, so go back over that those first sections if that's confusing. Okay, another type of question, example 2. Suppose that P is true and Q is false. Okay, so we have two propositions, but we're told their truth values. Find the truth value of this. Okay, so this is called a compound proposition. So you're connecting your basic propositions P and Q with logical operations. Okay, so yeah, this is just like working out a piece of arithmetic if you just had numbers. Okay, and yeah, just like arithmetic, yeah, we'll work out what's in parentheses first. So this P implies Q, is that true or false? Well, P is true and Q is false. So if you remember how implication works, then this is going to be false. Okay, so this piece is false. Yeah, this true implies false. Yeah, that's the only time that implication is false. Next we have a not. Okay, so not false is true. And then the last thing is this or operations. So we have something true or Q. Yeah, Q is false, so that's true or false, and that's true. Okay, so for or, if one of the two is true, then or both, then the whole thing is true. Okay, so we worked it out, and yeah, don't forget to say the answer clearly. Yeah, some of you are not doing that in the homework. And so then this compound proposition is true. We've answered the question. Yeah, so these truth values, again, it's either true or false. No other options. Okay, yeah, when you're talking about implications, so P implies Q, there are three related statements. Yeah, so people confused by this in the homework. So, yeah, P implies Q. If you start with that, then the converse is Q implies P, just switching the letters. The contrapositive is switching the letters and negating them. That's the contrapositive. And the inverse is keeping the same letters but negating them. So the inverse of P implies Q is not P implies not Q. Okay, and the original implication is equivalent to the contrapositive. So these are really the same. And these other two are logically different. Yeah, we'll get to that logical equivalence. Example 3, give the inverse of this statement. If it is not Sunday, then the post office is open. Okay, so we're starting with an implication. P implies Q. So P is saying it is not Sunday. Q is saying the post office is open. We want the inverse, so we're just going to negate each of these. Okay, so it is not Sunday. What's the negation of that? It is not the case that it's not Sunday. Well, that's just saying it is Sunday. It is not the case that the post office is open. The post office is closed. Okay, so in simple English, the inverse is saying if it is Sunday, then the post office is closed. All right, so that's the inverse of saying if it is not Sunday, then the post office is open. All right, but aren't these saying the same thing? Aren't these logically equivalent? No. So the original is saying, if it is not Sunday, then the post office is open. It's not telling you anything about Sunday. The post office could be open or closed. Okay, so we don't know that the post office is closed on Sunday. The post office might be open every day. All right, so I hope you see these are not equivalent. So if it is not Sunday, then the post office is open. The contrapositive of that would be the post office is. So yeah, you want the negative. So the post office is closed. So if the post office is closed, then it is Sunday. All right, so you can say that. All right, so if it is not Sunday, then the post office is open. It's equivalent to saying if the post office is closed, then it has to be Sunday. All right, that's the contrapositive. All right, we saw this application, the island of knights and knaves, or knights always just say true things, knaves always say false things. Okay, so example 4, you meet two people on this island. A says, I am a knight, and B is a knave. The second person, B, says, we're both knights. And the question is, can you decide if A and B, are they knights or knaves? Well, yeah, I mean, B is saying we're both knights. Well, if B is a knight, then that's true. So then A must be a knight. So A is saying, I am a knight, and B is a knave. Well, that can't be true if what B said was true. So yeah, there's a discrepancy here. So we can see they can't both be telling the truth. They can't both be knights. So one of them must be a knave. So therefore, what B said is not true. Okay, so B must be a knave. Okay, so logically, just looking at the possibilities, yeah, B has to be a knave. Yeah, we don't have enough information to pin down if A is a knight or a knave. So yeah, A could be a knight. So this could be a true statement. Or A could also be a knave. That also makes sense here. So if A says, I am a knight, and B is a knave, well, for that to be false, you just need this part to not be true, that he's a knight. Alright, so yeah, so for this example, all we can say is that B is definitely a knave, A could be either. Okay, next we looked at propositional equivalences in section 1.3. First, combinations of propositions that are always true are called tautologies. Example 5 show that this combination, this compound proposition, is always true. Okay, so first, so why is this always true? Well, if you look at this first part, P and not P. Okay, so whatever P is, these two guys have different truth values. So one of them is false, and we have an and here, so that means this whole thing has to be false. And we know from implication, if the first thing is false, then the implication is always true. Okay, so false implies P. So false implies false is true, false implies true is true. Alright, so that shows that this this compound proposition is always true, so it's a tautology. Yeah, in the homework, some people confused by this. Yeah, remember those truth tables? They're taking two different P's and P and a Q, two different propositions. It's simpler when you just have one proposition P here, so easier to figure out the cases. Really, there's only two cases here: either P is true or P is false. Okay, so now we know what a tautology is. The two propositions P and Q are logically equivalent if they always have the same truth value. So either P and Q are both true, or they're both false. They always have the same truth value. And in that case, we write P is equivalent to Q, so 3 lines. And it means, P if and only if Q is always true. Okay, so remember this if and only if it's true if P and Q have the same truth value. It's false if they have different truth values. So we're just saying the same thing in another way here. Alright, so example 6, use a truth table to show that not P and Q is equivalent to not P or not Q. Alright, so there are 4 possibilities for P and Q. So here are the 4 possibilities, so 4 rows. Okay, and then let's work out the left side. So first work out P and Q, and then just switch the truth value to get not P and Q. Alright, so the left side looks like this. Okay, then for the right side, we'll work out not P and not Q, and then take the OR. Okay, so for OR, if you have any T's, then it's true. If they're both false, then it's false. Okay, so the right side, that shows up here, and to be equivalent, we just have to be getting the same sequence of T's and F's. Yeah, so these are the same. Okay, so yeah, don't forget to interpret your table. So yeah, just point to these 2 rows and these 2 columns and say these columns are the same. So that means that we've proved that these are equivalent. They always have the same truth values. So yeah, so in other words, this if and only if this is always true. Okay, so you can prove things are logically equivalent by looking at all the cases using a truth table. Some other equivalences, yeah, these are the laws of logic. So we have this double negation, yeah, so not P, that's equivalent to P. P and Q, that's equivalent to Q and P. This is saying and is commutative. P and the quantity Q and R is equivalent to P and Q, quantity and R. This is saying that and is associative. Yeah, you have the same things for OR as well. Not P and Q is equivalent to not P or not Q. Yeah, we just saw that one. And also not P or Q is equivalent to not P and not Q. So when you take away the parentheses, the and changes to an or, and the or changes to an and. So those are called De Morgan's laws. And we also have a distributive type law. So P or Q and R is equivalent to P or Q and P and R. And yeah, so this is different from associativity. So here we have an or and an and, so we're combining two different operations here. So just like multiplication and addition. Okay, so we have these laws of logic. Yeah, there are more of them. Just a sample here. Alright, so that was propositional logic. Now we get into quantifiers in these sections. Okay, so we're introducing variables and functions now. A propositional function, p of x, it's either true or false, depending on what x is. So if you put in different x's, you'll get different truth values. And the x's that you're interested in, that's called the domain of discourse, or the universe. Okay, example 7. Let the domain be all real numbers, and let p of x say x squared plus 1 equals 10. Is p of 10 true? That's the first question. Second question, can we find an x that makes p of x true? Alright, so is p of 10 true? Well, if you put in 10 for x, it's saying 10 squared plus 1 equals 10. No, that doesn't look right. So that's false. So p of 10 is false. Can we find an x that works? In other words, can we solve this equation? Well, yeah, we can see that 3 is going to work. 3 squared is 9, plus 1 is 10. So p of 3 is true. Okay, so we can find an x that works. Okay, so yeah, if you want to talk about x's, which x's in the domain make something true, then you're getting into this idea of quantifiers. Okay, so we use this symbol for the universal quantifier. This upside down A. So the way to read this is for all x in the domain, we have p of x. Alright, so this is saying that p of x should be true for all x's, in this case for all real numbers. Okay, so in our example, the domain was all real numbers, and this is p of x. Okay, so what this means in this case is that for all real numbers x, we have x squared plus 1 equals 10. Okay, so the universal quantification of p of x is saying this. Well, is it true that for all real numbers, if you square them and add 1, you get 10? No, that's false. Okay, so these quantifications, they make a new proposition. So this whole thing it's either true or false. In this case, it's saying something that's false. Okay, the other main quantifier is the existential quantifier. It's backwards E. And the way to read this, it's saying there exists an x in the domain so that P of x okay, so in this example we're getting there exists a real number x so that x squared plus 1 equals 10. And yeah, we saw already that that's true. 3 works. Also negative 3 works. So the existential quantification of P of x is true in this case. Alright, here's some more complicated one with nested quantifiers, 2 variables. And yeah, we're using this notation, so instead of saying, yeah, we could have written this as, P of x comma y. And so a propositional function of 2 variables. But yeah, it's simpler here just to write what it's saying. Yeah, the domain here is still all real numbers, so this is saying for all real numbers x, there exists a real number y, so that 3x is equal to y. Okay, and again, this is going to be true or false. Okay, so again, it's saying, so for all real numbers x, there exists a real number y, so that 3x is equal to y. So is that true? I mean, for example, if x is 7, then 3 times 7 is 21. So yeah, there exists a y at 21. Yeah, so this is true. So it doesn't matter. So whatever x is, if you multiply by 3, you're going to get another number, and that's what y should be. So starting with any x, yeah, we can find a y. All right, so here we had quantification in two different variables for all, and there exists. We can negate quantifiers. All right, so if you wanted to negate this statement, so you want to say it's not the case that for all x there exists a y so that 3x equals y. Okay, so this negation, we put the not out front. But we can simplify this, so if you negate a for all, it becomes a there exists. And the not moves inside. And if you negate an existence, it switches to a for all, and the not moves inside. Okay, so you can simplify these negations. Okay, the quantifiers just switch. So the negation of this looks like this, with not 3x equal to y on the inside, so that's saying 3x is not equal to y. Okay, so then you can read this negation. It's saying there exists a real number x, so that for all real y, we have 3x not equal to y. All right, again, that's false. So yeah, the problem is when when say x is 7, this is 21. Well, is y not equal to 21 for all real numbers y? Well, no, when y is 21, then they are equal. All right, so this is false, but we knew it had to be false since the original guy was true. So if something's true, then its negation has to be false. Okay, but yeah, this is just illustrating how you negate these quantifiers. All right, and the last section we covered in this chapter was rules of inference. So so go back, take a look in chapter 1. Section 1.6. These rules, modus ponens. That's if P is true and P implies Q, then you can conclude that Q has to be true. And some more rules, modus tollens and hypothetical syllogism, and a few more. All right, so that's a quick look back at chapter 1.